Download this code from codegive.com, link in the description below. OK, let's dive into the world of binary synchronous communication, Bisync or BSC, a character-oriented synchronous data link protocol developed by IBM in the 1960s. We'll cover the protocol's features, structure, error handling, common control characters, advantages, disadvantages, and then provide a simplified code example to illustrate the core concepts. What is Bisync? Bisync is a half-duplex, character-oriented protocol for transmitting data synchronously between two devices. Synchronous means that both the sender and receiver use a common clock signal, either explicitly or implicitly derived from the data stream, to coordinate the transmission and reception of bits. Character-oriented means that data and control information are conveyed using specific characters defined in a character set, usually ebcdic or ascii. Half-duplex means that only one device can transmit at a time, the devices must take turns. Key features and concepts *. 1. Synchronous transmission *. Bisync relies on synchronization to maintain bit and character alignment. The transmission begins with synchronization characters, syn, to establish and maintain this timing. 2. Character-oriented * data and control are represented using characters from a defined character set. This simplifies parsing but also makes it less efficient than bit-oriented protocols. 3. Half-duplex communication * only one device can transmit data at any given time. This necessitates a mechanism for devices to request and relinquish control of the communication line. 4. Data framing * data is grouped into frames or messages. Each frame starts and ends with specific control characters that mark the beginning and end of the transmission. 5. Error detection * Bisync includes error detection mechanisms, primarily using checksums, example block check character or BCC, to verify the integrity of the transmitted data. If an error is detected, the receiver requests retransmission. 6. Control characters * Bisync relies heavily on special control characters to manage the communication process. These characters have predefined meanings within the protocol. Bisync frame structure *. A typical Bisync frame, or message, has the following structure. Let's break down each component. Syn, synchronization character. One or more syn characters are sent at the beginning of the transmission to establish and maintain synchronization between the sender and receiver. The receiver uses these to align its clock and character boundaries with the incoming data. Typically, 2 syn characters are used for initial synchronization. So, start of header optional. If present, so indicates the beginning of a header containing control information, example message routing, priority, destination address. Header, optional contains control information related to the message. The format of the header is not strictly defined by Bisync and can be customized based on the specific application. *stx, start of text marks the beginning of the data portion of the frame. *data * the actual information being transmitted. The data can be any binary or text data. *etb, end of transmission block indicates the end of a block of data. Typically used when the message is divided into multiple blocks. A BCC, block check character, follows. *itb, intermediate transmission block similar to ETB, but it indicates that more blocks will follow. ITB is often used when the data contains embedded transparency codes. A BCC follows. *etx, end of text indicates the end of the entire message. A BCC follows. *BCC, block check character, a checksum character used for error detection. It is calculated based on the data between the STX and the ETB/ITB/ETX. Common BCC calculation methods include longitudinal redundancy check, LRC, and cyclic redundancy check, CRC. Common Bisync control characters ***. Here's a table summarizing some of the most important Bisync control characters, using their ASCII representations. Note that ebcdic equivalents also exist and are often used in IBM environments. Control character ASCII hex description. Syn16 synchronization. Used to establish and maintain bit and character synchronization. So01 start of header. Indicates the beginning of a header. STX02 start of text. Indicates the beginning of the data portion of the message. ETX03 end of text. Indicates the end of the message. EOT04 end of transmission. Indicates the end of a complete transmission sequence. ENQ05 inquiry. Used to solicit a response from the receiver. AC06 acknowledge. Positive acknowledgement indicating successful reception. DLE10 data link escape. Used to introduce transparency codes or special control sequences. NAK15 negative acknowledge. Indicates that an error was detected and retransmission is requested. ETB17 end of transmission block. Indicates the end of a block of data. ITB18 intermediate transmission block. Indicates more blocks will follow. Sub26 substitute. Replaces an invalid or unacceptable character. BCC varies block check character. Error detection checksum. Error handling ***. Bisync relies on the BCC, block check character, for error detection. The BCC is calculated by the sender and appended to the end of each block or message. The receiver independently calculates the BCC based on the received data and compares its calculated BCC with the received BCC. No error if the calculated BCC matches the received BCC, the receiver sends an acknowledge character to the sender, indicating successful reception. Error detected if the calculated BCC does not match the received BCC, the receiver sends a NAK, negative acknowledge, character to the sender, indicating that an error was detected. The sender then retransmits the block or message. Transparency Bisync sometimes needs to transmit data that includes characters that would otherwise be interpreted as control characters. To handle this, Bisync uses a technique called transparency. The DLE, data link escape, character is used to escape control characters within the data stream. When the receiver encounters a DLE character, it interprets the following character literally, even if it is a control character. For example, if you need to send the actual ETX character within the data, you would send DLE ETX. The receiver would interpret this as the character ETX rather than the end of text control sequence. Handshaking and polling/selecting ***. Handshaking * Bisync uses ENQ, inquiry, and ACK/NAK, acknowledge/negative acknowledge, characters for handshaking to establish a connection and manage the flow of data. Polling/selecting in multi-drop configurations, where multiple devices share a single communication line, Bisync often uses polling and selecting. A central controller polls each device in turn to see if it has data to transmit. The controller selects a specific device to receive data. This is done using specific addressing and control characters. Advantages of Bisync ***. Simplicity * relatively simple to implement compared to more modern protocols. Wide availability * was widely used and well understood, especially in older systems. Character-based easier to debug and troubleshoot, because data is character-oriented. Disadvantages of Bisync inefficiency character-oriented nature leads to higher overhead compared to bit-oriented protocols. Control characters and transparency mechanisms increase the amount of data transmitted. Half-duplex half-duplex operation limits the throughput. Only one device can transmit at a time. Limited error recovery error recovery is relatively basic, retransmission. Lack of standardization variations exist in the implementation of Bisync, which can lead to interoperability problems. Not suitable for modern networks Bisync is not well suited for modern, high-speed, full-duplex networks. It has been largely replaced by more efficient protocols. Simplified code example, Python. This is a highly simplified Python example to illustrate the basic principles. It does not implement all the features of Bisync, error detection, transparency, complex handshaking, etc., and is intended for educational purposes only. Real-world Bisync implementations are much more complex. Explanation of the code *. 1 Control characters *. The code defines the ASCII hex values for the SYN, STX, ETX, ACK, and NAK control characters. 2 Bisync device class *. *_init__ initializes a Bisync device object. The is_sender flag indicates whether the device is intended to send or receive data. It also initializes an empty data buffer to accumulate received data. *send_data constructs a Bisync frame with SYN characters, STX, the data, and ETX. It prints the hex representation of the message for debugging. *receive_data simulates receiving data. It checks for the correct frame format, STX, ETX, extracts the data, and returns ACK or NAK. *synchronize, this simulates the startup where the device sends out SYN characters so that the other side can sync up. 3 Example usage *. Creates sender and receiver instances. * Simulates sending and receiving data. * Prints the results. Important considerations Error handling is missing This example lacks proper error handling, BCC calculation, NAK handling, retransmission. A real Bisync implementation would require robust error detection and recovery mechanisms. Transparency is missing This example does not handle transparency. If the data contains control characters, you'll need to implement DLE insertion/removal. Half-duplex implementation The example doesn't explicitly handle half-duplex switching, example using ENQ to request the line and EOT to release it. A real Bisync system would require a mechanism to manage who has the right to transmit. Hardware dependencies This is a software simulation. A real Bisync implementation would need to interface with serial communication hardware, example UART, to send and receive data at the bit level. Conclusion Bisync is a historically important protocol, but it's largely obsolete in modern networking. Understanding its principles can be helpful for understanding the evolution of data communication and for working with legacy systems. This tutorial provided a comprehensive overview of Bisync, including its features, frame structure, control characters, error handling, advantages, disadvantages, and a simplified code example. Remember that a real-world implementation would be significantly more complex, handling error detection, transparency, and half-duplex operation in a more robust way.